Okay, welcome back. Welcome back. We were looking at Hamming code, and we said that Hamming code is an example of error correction code, or in some cases, you can say detection correction code, developed by Richard Hamming. Okay, um, we are given a message, which in this case is 1011, and we are supposed to calculate the Hamming code. Now, the essence of doing all this is this, right? So assume a scenario where you want to store this message within a storage device, or maybe you want to send it somewhere, you want to transfer. You want to ensure that whatever you've sent or whatever you've stored or whatever you've saved is still the same thing next time you try to access it. Okay, so if you saved it, next time you try to retrieve it, it's still the same data. Or if you sent it from a sender to a receiver, you want to make sure that whatever is sent by the sender is the same as what is received by the receiver. Okay, so what we are doing is that we are adding some extra bits, what we are calling the redundant bits, within our message bits, okay, so that we can be able to confirm that whatever we've received or whatever we are trying to retrieve from our message, from our storage device, is the same thing that was saved there. Okay, and we came to understand that we are going to be using three steps. Number one, we were to calculate the number of redundant bits, which we used a formula. Okay, then number two, we were able to know the position of those redundant bits. Okay, so knowing the position was based on us understanding that those redundant bits are going to be at the powers of 2. Okay, so after identifying the number of redundant bits, which is found was 3, okay, we were able to understand that the total number of bits we are going to be having is 7. So we just wrote down those positions, okay, starting from the right hand side to the left, and then we said that the powers of 2 are going to locate our redundant bits. Sorry. So after that, we then filled the remaining positions with the message bits in the order to which those bits appear. Okay, so now the third step was to calculate the value of these redundant bits. Remember, when I talk about this, I'm saying yes, we've already identified their position, but we don't know what they are. Are they 1 or 0? Okay, or are they 0 or 1? That is what I mean, because in this case it's a binary option, right? It's either one or the other. It's either 0 or 1. So to calculate the value, we first start by understanding that in this case the redundant bits are parity bits. Okay, and a parity bit is, it's an extra bit that is used to make the number of ones in a given set of bits either even or odd. Okay, it's a very common technique that you'll find within the computing field. Okay, so we are going to be adding extra bits. Okay, so this is the reason why we are calling it redundant bits, and they are still the same as parity bits. So when you add these ones, you are supposed to add these redundant bits in the consideration of whether you want to have the total number of ones. For instance, in this particular setup of message and redundant bits, where you have either an even number of ones or an odd number of ones. Okay, and each of these redundant bits that we have here, R1, R2, R4, okay, the way we calculate it is based upon its position. So if it's at this position 1, okay, we'll consider all those bits, okay, where within the first position, and maybe this one is a bit difficult to explain without having gone back a little bit. Okay, without going back a little bit. So if you recall, when you are converting between decimal and binary, okay, decimal and binary, you must have been given this shortcut of the 8421 code, okay, where you are able to translate from decimal to binary, and the shortcut was that you wrote this one down, and then below them you followed based on the numbers given at the top. So for instance, if it was 8, you wrote 8 zeros first, and then you wrote 8 ones. Then in the next column, I need that one to go away. In the next column, you had 4 zeros, 4 ones following each other until the end. So you repeat that until you get to the point where the 8 zeros and the 8 ones end. And then for the third column over here, you had 2 zeros and 2 ones all the way until to the end. And then for 1, you had 0 1 0 1 0 1. Now in case that is not clearer, maybe a comment can be made and we can make another video on that. Anyway, to make the long story short, you're going to find that R1, okay, is going to be determined by the following set of bits. It's going to be determined by the bit 1 itself, okay, and I'll show you what I mean, even though we can say that the position 1 is exempted because it's actually the position that we don't know. But anyway, it's going to be 1, and then you're also going to consider position 3, and also you're also going to consider position 5, you're also going to consider position 7 and others. So for this case, as you can see, we stop at position 7 because that is all that is covered within the data that we have right now. Okay? Then for R2, it's determined by 2, okay, but obviously we are going to say that one is exempted because it's what we don't know. And then the other bits are going to be 3 and then 6 and then 7, among others. Okay, so if you have more redundant bits, you may need to consider that. Sorry, not redundant bits. If you have more message bits, okay, and actually you'll even have more redundant bits, you may need to consider beyond 7. But for now, we stop. Then for, let me just scroll down a bit. Then for R3, you're going to consider 3, but then again, like we've said, we're going to exempt ourselves from the third one, but then we have that. So we are going to still consider, sorry, this is R4. I always make this mistake. It's R4. It's always R4, okay, because remember it's position 4. You don't want to have that mistake of thinking of R3, okay, because you may put yourself in that situation where you are considering the third redundant bit being at position 3. So it's always important to call it as R4 so that you don't forget that. So in this case, you're going to consider bit number 4, which in this case we're going to exclude because we don't know its value. And then the next one is going to be 5, 6, and 7. So these ones just follow each other. In case you're able to come up with that table, and maybe I'll try and do that in the next video, you'll be able to see how these bits are being considered. Okay, they are being considered. So anyway, so for us to be able to calculate now, given R1, okay, so for R1, for instance, we are talking about us excluding the first position. So we are going to say that we don't know what the first position is. Allow me to use the first position with X, okay, so we don't know X in this case, but do we know what is at position 3? Okay, so we do know what is at position 3. In this case, it's a 1. Okay, and what is at position 5? Position 5 has 1. Okay, and then what is at position 7? Position 7 has a 1 as well. Okay, so luckily for us in this case it's just 1 1 1 1. I don't know whether it's a good thing or bad thing, but we'll be able to see that one in a short while. So the next step for us to be able to know the value of R1 is to know whether we are considering even parity or odd parity. Because if we are considering even parity, then we want to make sure that within this combination of these 4 bits, okay, we are going to have an even number of 1. Okay, but if we are considering odd parity, we also need to make sure that within this combination of bits we have an odd number of 1s. Okay, so let us consider that we are having even parity. So considering even parity. Okay, so what that means is within this combination of 4 bits we need to make sure that we have an even number of 1s. Okay, so as you can see, we already have 3 1s. So directly X needs to be 1 so that we can have an even number of 1s. So in this case, my R1 will be 1. So X is going to be 1. Okay, so that's how we know the value of R1, because X can only be 1 for it to be even, for this combination of these 4 bits to be even. If we put a 0, there will be an odd number, and as you can see, we've already designated that we require even parity. So in that case, my R1 is going to be 1. Okay, then we do the same thing with these others now, right? So we don't know 2 positions, so that's why we said we are excluding it, but then we do know what 3 is. 3 is 1, and what is 6? It's 0, and then what is 7? 7 is 1. So given that combination and the existing ones that are there, okay, what is the value of X so that we can have an even number of 1s within this combination of 4 bits? Okay, so obviously X should be 0, because if you make it to be 1, you'll have an odd number of 1s. So my X in this case should be 0. So my R2 is going to be 0. Then we go to the next one, that is R4. Okay, so we don't know what position 4 is. R4, we don't know what R4 is. So in that case, we can exclude that position 4, but then we do know what 5 is. So position 5 has 1. Okay, position 6 has 0, as you can see. Okay, and then position 7 has 1 as well. Okay, so again I ask, so you want to have an even number of 1s in this case. Okay, so what do you make X to be? Is it a 0 or 1 so that you can have an even number of 1s? Okay, so obviously it should be a 0 so that you can have an even number of 1s, because if you put it as 1, then obviously you're going to have an odd number of 1s. So in this case, my R4 is going to be a 0. Okay, simple and clear. Okay, so now to end it all, you can just come back and maybe using the place values that we had. We've already known that here we had 1, here we have 0, here we have 1. Okay, I'm just following the setup that we had here. Here we had R4, which you didn't know, and then here we had 1, and then here we had R2, and then here we had R1. So we are just going to replace their values as we've been able to calculate them. So R4 was 0, so I can replace this one with 0. Okay, and then R2, as you can see here, is 0 as well. I'm also going to make it 0. And then R1 was 1, so I'm going to replace that one with 1. So if you are to write now the entire Hamming code as it's going to appear, it's going to be 10 10 101. Okay, so these are 7 bits if you are to check. Okay, these are 7 bits, and that is the Hamming code in this case. So instead of maybe saving or maybe writing in memory just the message bit as 1011, now for us to be able to detect and maybe correct errors when we are saving this message or we are transferring this message, we are going to put this all together, the 7 bits, and using those redundant bits, we are going to be able to identify whether we have errors as we try to retrieve our data or as we try to receive our data. So in the next video, we are going to use those redundant bits, or we are going to see how we use those redundant bits to detect and eventually correct errors if any exist.